Assalamu alaikum. So today we will discuss modeling of synchronous machine. Let's assume that we're having three-phase synchronous machine, and let's assume this is the phase A, the start and the end of the phase A. Here the current is out, here the current is in, so this will be AS dash. So this will be the axis of the AS. In the same fashion, let's assume that here we're having the phase B. So this is the BS dash BS, and this will be the phase BS, and let's assume this is the CS. So this will be the CS axis. And let's assume that we have a salient rotor in which the air gap is not uniform. Let's assume this is our rotor, and in this rotor let's assume we have a field coil. This is the start and the end of the field coil. So this will be the axis of the D axis, the field axis, and let's assume we have a damper winding also in the direction of the D axis. So this is also a damper winding. The damper winding is similar to the squirrel cage induction machine. It's actually bars shorted by a ring. We install it in the synchronous machine in order to provide starting torque, because the synchronous machine has no starting torque in general. So this will be the start and the end of the damper winding. And let's assume that we also have two damper winding in the Q axis. So let's assume this is the first damper winding, KQ1, and the second damper winding, KQ2. So this will be KQ1 dash, and this will be the KQ2 dash. Now here FD stand for field winding, and KD stand for damper winding acting in a D axis. So this is damper winding acting in the D axis, in the direction of the axis, of course. Now we have also two damper winding in the Q axis, which is the KQ1 and KQ2. Those are two damper winding, acting in the direction of the QX. Now, this is by definition we call the magnetic axe of the field winding. So dx is actually called the magnetic axe of the field winding. So this is called the magnetic axe of the field winding. Now, the Dunbar winding actually is similar to squirrel cage structure, and we use it in order to provide starting torque. For the synchronous machine. So if this is the rotor, and the Dunbar winding is similar to a squirrel cage, and here we have the which is the Dunbar winding. Now, why we need the Dunbar winding? In general, we need the Dunbar winding to provide starting torque. Now, why the synchronous machine does not has starting torque? Simply, if we recall a two-pole machine, let's assume this is the north, this is the south, and here let's assume that this is a revolving magnetic field. So let's assume at t equal to 0 we have the following location. This is the in, this is the south. Now in the rotor we have field winding, and those field winding is let's say those field winding is supplied by a DC current. So those are supplied by DC current. So simply we have here stationary pole on the rotor. So the field winding will generate stationary pole. Let's assume this is the north and this is the south. Now at t equal to 0 the south will try to catch the north, and the north will try to catch the south, but before even the rotor is rotating, the magnetic pole for the stator is changing. Now here will become south and here will become north. Why? Because those are alternating in the in the frequency of the stator. So the rotor has inertia, which means that it needed time in order to speed up, and this time is very short compared to the electrical time constant. So in this case, the machine will never rotate. In order to provide a starting torque, we will implement in the rotor the damper winding, and the damper winding would act as a squirrel cage. So simply at start, the machine will operate as induction machine. Then near synchronization, when we engage or supply the field to the rotor, after that the rotor will rotate near the synchronous speed. Then the north will catch the south, and the south will catch the north, and they will start rotating in synchronous speed forever after. Now, if we plot here the circuit for the synchronous machine, the three-phase Y-connected salient coil synchronous machine, let's assume that this is the stator, and this is the phase. Let's assume this is IAS, and let's assume this is the IBS, and let's assume this is the ICS. So this will be RS, this will be the RS, this will be the RS, which is the stator resistance. This will be the NS, the equivalent term of the stator winding. So this will be plus minus, plus minus, plus minus. So this will be the VAS, this will be the VBS, and this will be the VCS. Now this is the stator circuit. For the rotor, we have four winding, two in the direction of the D-ax, which is the field winding, and the first damper winding in the D-ax. So simply here we can plot the first damper winding, and this is the second damper winding, and both are acting in the direction of the D-ax. So let's assume this is plus minus VKD. So this will be RKD, and this will be the NKD. The same thing, let's assume this is plus minus VFD. So this will be the RFD, and this will be the NFD. Now in the direction of the Q, also we have two damper winding. Let's assume this is the first one, and this is the second one. So here this will be plus minus VKQ1, this will be plus minus VKQ2, this will be the RKQ1, NKQ1, NKQ2, and this will be the RKQ2. And remember here, and stand for the equivalent turns number. So this is actually a 2-pole 3-phase Y connected or star connected, let's say, salient pole synchronous machine. Now the voltage equation in machine variable can be written as now remember, if I need to model any electrical machine, I need to find the voltage equation, and I need to find the electromechanical torque, and finally I need to find or to write the swing equation, and this will complete the mathematical model of an electrical machine. So in the same way we did it for the induction machine, here I will say that VABCS, and SCS stands for the stator, is equal RSIABCS plus d by dt of lambda ABCS, which actually Ohm law plus Farad law of induction. Now in the same fashion here, the rotor circuit actually is orthogonal. So here we have VQ dr equal to RR IQ dr plus d by dt of lambda Q dr. And here S is stand for the stator, and R stand for the rotor circuit. Now here I'm using the notation where FABCS transpose will equal to FAS, FBS, FCS, and F can be any function. It can be flux, it can be voltage, it can be current. Now the same thing here, FQDR transpose will equal to FKQ1, FKQ2, FD, let's say, and FKD, where F here can be any function. So it can be current, voltage, or a flux linkage. Now this is RS and RR here. Now RS actually is diagonal matrix, so we can write diagonal of RS, 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 and RR is also a diagonal matrix, so this will be diagonal of RKQ1, RKQ2, RFD, and finally RKD. Now the flux linkage, in order to write the voltage equation, we need to find the flux linkage, lambda ABCS and lambda QDR. Now assuming a linear magnetic circuit, we can write the flux linkage as follow: lambda A B C S lambda Q dr will equal to LS LSR LSR transpose LR multiplied by the current IABCS and IQDR. Now remember, in linear magnetic circuit we are assuming that the flux linkage can be written as Li. So simply here, lambda ABCS, we have two flux linkage. One is due to the stator and the second one is due to the rotor circuit. The same thing is valid also for the rotor circuit. Now we need to find LS, LSR, and LR in order to find the voltage equation. Now for simplicity, let's assume that we have only one damper winding in the Q ax and one damper winding in the D ax. So here, for simplicity, let's assume we have only two damper winding, one in the direction of the Q, so this will be the KQ, and one in the direction of the D, so this will be the KD. So lambda ABCS, which will equal to lambda AS, lambda BS, lambda CS, equal to, now this will be the LS, the self-inductance, multiplied by IABCS plus the mutual inductance, or the inductance between the stator and the rotor, the mutual inductance between the stator and the rotor, which is the LSR. So this will be the LSR IQDR. So this can be written as lambda AS, lambda BS, lambda CS, and now LS is LAAS, LABS, LACS, LBAS, LBBS, and here we have the LBCS. Here this will be the LCAS, this will be the LCBS, and this will be the LCCS. This is actually the LS. Now we also have having the LAKQ, LAFD, and we have the LAKD. This should multiply here by the current, which is the IAS, IBS, ICS, and here we having the IKQ, the IFD, and the IKD. So simply here this will be phase B, and this the first one in the KQ current. So this will be the LBKQ, this will be the LBFD, this will be the LBKD, D. Now this will be the LCKQ. This will be the inductance value, which is the LCFD, and this will be the LCKD. So this actually is the LS, and this actually is the LSR. So this is the self-inductance of the synchronous machine, and this is the mutual inductance between the stator and the rotor. So now we need to calculate the self-inductance, and we need to calculate the mutual inductance. So let's start to calculate the LS, which is the stator self-inductance. Now, in general, the self-inductance, which is the LAAS, consists of two parts. One is called the leakage inductance, plus the magnetizing inductance or the air gap inductance. The second one we call plus the magnetizing. Or sometimes we call it the air gap inductance. So simply, this means that LAAS will equal LAL, the leakage inductance, plus LAG, the magnetizing inductance or the air gap inductance. Now, let's calculate the LAAS. So, let's assume this is the phase A, this is AS, and here we are injecting a current. Let's assume this current is equal to IAS. And let's assume that this is the direction of the rotor. And this is the Q, and this is the DX, and the rotor is rotating by omega r speed. So now injecting current in phase A will induce magnet motive force. So the first thing, the MMF will be generated in phase A. So the MMF along AS, according to the Ampere law, will equal to NS IAS. Now, this MMF in the direction of phase A will induce MMF in the direction of the Q and the D. So, the MMF along the QX will equal to the MMF along of AS multiplied by cosine of the angle, and the angle between AS and QS, this angle is theta r. So this will be cosine theta r. So this will equal to NS IAS cosine theta r. Now, in the same fashion, the MMF along the dx will equal to, now the angle here, this angle is equal pi over 2 minus theta r. So it will be the MMF along the AS multiplied by cosine the angle in between, which is the theta r minus pi over 2, and this will equal to ns IAS sine theta. Now recall, cosine of minus theta is equal to cosine of theta, and cosine of theta minus pi over 2 is equal sine of theta. Now let's track the flux along the q-axis. So here we can write the flux along the q-axis, which is phi q will equal the MMF of the q over the reluctance, which will equal to the MMF of the q multiplied by the permeance, where the permeance is equal 1 over the reluctance, and P here stands for the permeance. So the flux along the q-axis phi q will equal to ns IAS cosine theta r multiplied by the permeance of the gap in the q-axis. Now the same thing we can write the phi d, which equal ns IAS sine of theta r multiplied by the permeance of the d axis of the gap. Now the flux linkage lambda is equal in phi, so the flux linkage along the q-axis will equal n s multiplied by phi q-s, so this will be the ns square IAS cosine theta r, the permeance along the q of the gap. The same thing here, if I need to write the flux linkage in along the d axis, this will equal ns square IAS sine theta r multiplied by the permeance along the d of the gap. Now here we're having one flux linkage here, lambda q s, and another flux linkage here, which is lambda ds. If we need to have their projection along the AS, we need to multiply by the cosine of the angle in between. So simply lambda A on the gap will equal to NS IAS cosine theta r PQG multiplied by cosine theta r, so here square, plus ns square IAS sine square theta r, the p in the direction of the d, the gap. So now we can calculate now the air gap inductance, or the magnetizing inductance, which is the LAG, which equal the lambda AG over IAS. So this will equal to NS square cosine square theta r PQG plus NS square sine square theta r PDG. Now we can use the following trigonometric identity. In order to simplify the magnetizing inductance. So we can use sine square theta equal to 1 minus cosine 2 theta over 2, and cosine square theta equal 1 plus cosine 2 theta over 2. So if we do so, then the magnetizing inductance, the LAG, will equal to NS square multiplied by PQG over 2 cosine 2 theta r plus 1 plus PDG multiply over 2 multiply by 1 minus cosine 2 theta r. So collecting the terms, we are getting this will equal to NS PQG plus PDG over 2 minus NS squared PDG minus PQG over 2 multiplied by cosine double of the angle, cosine 2 theta r. Now we can define this one as LA, and we can define this factor here as LB. So to this end, we can write the magnetizing inductance, the LAG, equal to LA minus LB cosine 2 theta r. Now, if we compare here LA with LB, we can note that LA is greater than LB, and this is for salient machine when LD not equal to the L cube. So this is called salient machine, or simply a non-uniform air gap, called the non-uniform air gap. But for cylindrical rotor, for cylindrical rotor, in this case the rotor rotates, the gap is uniform, so LD will equal to LQ, and in this case LB will equal to 0. So for cylindrical rotor or wound rotor, the permeance, the PQG will equal to the PDG, which means that the inductance along the D axis will equal the inductance along the Q axis, and in this case we'll end up the magnetizing inductance is constant value equal to NS square PQG plus PDG over 2, which means that the inductance depends only on geometry, and this is the conclusion that we reach in the induction machine. However, here we are discussing a salient wheel, the salient. In this case, the rotor is salient, so simply there is the gap is non-uniform. In this case, we have the self-inductance is function also of the position of the rotor. Now let's calculate for example the LAB, but before that this is the self-inductance for the phase A. So in the same fashion the self-inductance for the phase B and the C we can calculate. So in the same fashion we have the LBBS will equal LLS plus LA minus LB cosine 2 theta r minus 2 pi over 3, and LCCS will equal LLS plus LA minus LB cosine 2 of theta r plus 2 pi over 3. Now let's calculate the mutual inductance. Let's say the LAB, which equal LBA. So simply this actually we are trying to find the stator mutual inductance or simply the mutual inductance between the two phases of the stator. So the mutual inductance between two phases of the stator. So for that, let's calculate LAB or LBA. So here, let's assume that this is the AS, and this is the BS, and this is the CS. Let's assume this is the rotor, and this is the direction. So this is the Q axis, and this is the D axis, and the rotor is rotating by omega r speed. Now the angle between here and here is theta r. Now you know that if I need to calculate LAB or LBA, I need to find either the lambda AB or the lambda BA. Then I need to divide over the current that caused the flux linkage. Here, let's assume that I'm injecting a current in the A-axis. So let's assume here I'm injecting the current uh, in A phase direction. So this will be IAS. Then I will measure the flux in the direction of the B. Then I will divide it over IA in order to find the mutual inductance between phase A and phase B. So now if we need to find lambda AB, this will equal, or let's write it here. So lambda AB will equal to NS IAS, and this is the MMF in the direction of the AS. Then cosine theta r, this is the MMF in the direction of the Q. So this one here is the MMF in the direction of the AS. Now this one here is the MMF in the direction of the QS. So if we multiply it now by the permeance of the Q of the gap, so this actually will be the flux linkage in the direction of the flux in the direction of the QS. Now if we multiply it by NS, this would be the flux linkage lambda QS. Now if we multiply it by, if we project it, let's say, to the phase B. Now if we need to project it to the phase B, we need to multiply it by cosine the angle between the Q axis and the B axis. So this will be cosine theta r minus 2 pi over 3. Now the angle between here and here is actually 2 pi over 3 minus theta r, and you know that cosine of minus theta is equal cosine of theta. So this actually here now is the projection of the QX flux in the direction of the B. But remember, here we have two components, one in the Q X, and the second one in the D X. So here also we have plus NS IAS sine theta r PDG cosine. Now the angle here is the angle between the D and the B here is 2 pi over 3 cosine 2 pi over 3 plus pi over 2 minus theta. So the angle here will be the 2 pi over 3 plus pi over 2 minus theta. So simply This is the angle. So this will be the contribution of the d-axis flux on the b-axis flux. Now also this one here can be simplified to be sine the theta r minus 2 pi over 3. So now we can write the lambda AB equal to I S NS cosine theta r PQG cosine theta r minus 2 pi over 3 plus IAS NS sine theta r sine theta r minus 2 pi over 3 multiplied by the permeance in the direction of the D of the gap. Now if we need to calculate the inductance, LAB will equal to lambda AB over IAS, which will equal to minus 1 over 2 LA minus LB cosine 2 multiplied by theta r minus pi over 3. Now here I used two trigonometric identity in order to simplify the flux. So here I'm using the sine alpha sine beta is equal to 1 over 2 cosine alpha minus beta minus cosine alpha plus beta, and also we need cosine alpha cosine beta equal to 1 over 2 multiplied by cosine alpha minus beta plus cosine alpha plus beta. Now in the same fashion we can calculate the LAC, which equal to LCA, and this will equal to minus 1 over 2 LA minus LB cosine 2 of theta r plus pi over 3, and LBC will equal LCB equal minus 1 over 2 LA minus LB cosine theta r plus pi. So this will finish the self-inductance of the stator for the synchronous machine, salient pole synchronous machine. Now we can calculate also the mutual inductance between the stator and the rotor, which is the LSR. So here the mutual inductance between the stator circuit and the rotor circuit, the stator and the rotor. Now remember here, this is the rotor. So this is the Q axis of the rotor, this is the D axis of the rotor, and this is the AS. The rotor is rotating by omega r. So the angle here is theta r. Let's assume here we have a coil, which is the ES coil. So now we need to calculate the LSR, which actually the LAKQ, the LAFD, LAKD, and so on. Now simply here the angle between AS and QS is theta r. So simply this means that the LAKQ will equal LSKQ, certain inductance between the stator and the rotor when the two phases are elegant to each other, then multiply by cosine the angle in between, which is cosine theta r. The same thing here, we can calculate the LAFD, which will equal the LSFD. Now cosine the angle in between. The angle in between is pi over 2 minus theta r. Now this is the angle that we are speaking about. So this angle is pi over 2 minus theta r. So this will equal to LSFD sine theta r. Now also we can calculate the LAKD, which will equal to LSK cosine the angle in between, which is the pi over 2 minus theta r, which will equal the LSKD sine theta r. And so on. We can calculate all the elements in the mutual inductance between the stator and the rotor. So if we do so, we will end up with LSR equal to LSKQ cosine theta r, LSFD sine theta r, LSKD sine theta r. Now here we have the LSKQ cosine, so I will see for that cosine theta 1, and here I will define C as the cosine and theta 1 and theta 1 as theta r minus 2 pi over 3, and theta 2 as theta r plus 2 pi over 3, and also here I will define S as a sine in order to manage the space, So this will be the LSFD sine theta r minus 2 pi 3, so theta 1, and this will be the LSKD sine theta 1, so this will be the LSKQ cosine theta r plus 2 by 3, and we already defined as theta r 2, theta r plus 2 pi over 3 equal theta 2, and this will be the LSFD sine theta 2, and finally here we have the LSKD sine theta 2. Now finally we need to write the rotor self-inductance. So here the rotor self-inductance, which is the LR. Now remember, the rotor consists of two phases which are orthogonal, sorry. So simply here there is no interaction between the D and the Q. So LR will equal to LL KQ plus LM KQ, and this is the self-inductance of the damper winding acting along the QX. There's no relation with the DX because the coils on the rotor are orthogonal. So this will be the LLFD plus LMFD, and this will be the LLKD plus LMKD. Now, in the DX of the rotor, we have two windings. One is the field winding, and the other one is the damper winding acting along the DX. So here we have mutual inductance between them. So here we will have the LFD-KD, and this will be the LFD-KD. Now, if we define the following magnetizing inductance, so here we can define the LMQ equal to 3 over 2 LA minus LB. The LMD equal 3 over 2 LA plus LB. And also we can define the LSKQ equal to NKQ over NS, the ratio of the turns of the damper winding of the K over the stator equivalent turns multiplied by 2 over 3 LMD. LSKD will equal to NKD over NS, 2 over 3 LMD, and so on. So we also can write here the LMKQ equal to NKQ over NS squared 2 over 3 LMQ, and here we can write LMFD equal to NFD over NS squared 2 over 3 LMD, and finally here LMKD equal to NKD over NS squared 2 over 3 LMD. And finally here we have the mutual inductance between the field and the DX, damper winding acting on the DX, which is the LFD KD. This will equal the NFD over NKD multiplied by LMKD. Now we need to refer the rotor circuit to the stator circuit. So referring the rotor circuit to the stator, so Ij dash will equal to 2 over 3 Nj over Ns multiplied by Ij. So here J can be the FD, KD, KQ. And dash here mean that the current is referred to the stator circuit. Now you know that referring should not change the power balance, so simply this means that Vj dash must equal to Ns over Nj multiplied by Vj. Now the flux linkage is acting in the same direction of the voltage, so Vj dash will equal to Ns over Nj lambda j. So referring to the stator circuit, the flux linkage can be written as so here we have lambda ABCS, here we have lambda QDR dash, and dash mean that the rotor circuit is referred to the stator circuit, so this will be the LS here, this will be the LSR dash, this will be the 2/3 LSR dash transpose, and this will be the LR dash, and here we have the IABCS, and here we have the IQ dash DR. Dash. So simply we can write now the LSR dash equal to LMQ cosine theta R LMD sine theta R LMD sine theta R LMQ cosine theta 1, and remember theta 1 is defined to be theta R minus 2 pi over 3. This will be the LMD sine theta 1 and this will be the LMD sine theta 1. This will be the LMQ cosine theta 2. This will be the LMD sine theta 2, and remember theta 2 was defined to be theta R plus 2 pi over 3, and this will be the LMD sine theta 2. Now the LR dash will equal to LLKQ dash plus LMQ 0 and 0 0. Here we have the LFD dash plus LMD. Here we have LMD. Here we have the LMD, here the 0. And finally here we have the LLKD dash plus LMD. So now the voltage equation expressed in terms of the machine variable, it can be written as, so in machine variable, the voltage equation can be written as VA BCS VQ DR dash equal to RS here plus D by dt of LS D by dt of LSR dash. Here we have 2/3 D by dt of LSR dash transpose, and here we have the RR dash plus D by dt of LR dash multiplied by the current, which is the IABCS the IQDR dash. Now RJ dash, which is the resistance referred, the rotor resistance referred to the stator, is equal to 3/2 NS over NJ squared RJ, and J here can be the KQ, KD or FD, and the inductance which is the LIJ dash equal to 3/2 NS over NJ squared Lij. So now in order to finish the modeling, we need to find the torque, and simply the torque Te will equal the partial omega c by partial theta m when I is constant. So simply here we can calculate the torque Te equal to P over 2 in order to use the electrical angle instead of the mechanical angle, because this is a mechanical angle and they are related by P over 2. So this will equal to 1 over 2 IABCS transpose partial by partial theta R L S IABCS plus IABCS transpose partial LSR by partial theta R IQ dr dash. And simply we need to write the swing equation. Which is the J d omega by dt plus b omega is equal Te minus TL. And in this case we are finishing the model in machine variable. Next time I will discuss with you the model of the synchronous machine in the arbitrary reference frame. So